Good afternoon. This is Andy from Yahoo, and today I would like to share with you some of the open source project we released several months back called TensorFlow on Spark. Essentially tried to do the deep learning in Spark clusters. So the way, I guess I will try to give you high level, low level things, but if you want to just dive deep into it, I'm happy to jump into whatever the section you want. So again, it's an open source code, so you could check out the code at the GitHub. So the idea here is, you have TensorFlow, you could run in dedicated clusters, but what if you want to have using the data, you're using the computation powers in your Spark cluster, or you want to combine all the Spark capability in with your deep learning things, what are you going to do? So this is the framework we designed. The effort we started was late last year, and currently it's heavily utilized at Yahoo. It's one of our most popular framework inside this company. So you may wonder, why you decided to do that. I think partially it's the history of the Yahoo thing, right? So we early on, if you know, the Hadoop thing was come from our group, and then later on there was the Spark stuff. We are kind of one of the early adopters. I was on the stage in the first Spark summit to say, yeah, Spark is great. Even so, it's just to say, and then the 2016, we also released another open source project called the Cafe on Spark. So in some ways, the TensorFlow on Spark is simply built on top of the lessons we have learned over the years. And it's a relatively simple effort for us. But we just want to use this as an opportunity to work with the community. And as I mentioned earlier on, in Yahoo environment, for example, right, we have the massive. I think we may have one of the largest Hadoop clusters. So we have like tens of thousands of machines in it, and then so in that environment, we almost all of our data about our user, about our product, all those things actually is already on our Hadoop cluster, right? So in such a kind of environment, we just wanted to enable our deep learning scientists be able to do their job right away. So here is what was happening before we introduced the TensorFlow on Spark, right? So what happening here is that we have the Hadoop cluster in the one side, have the Hadoop Spark capability in it. Then the other side, for the deep learning side, they put it together like a few GPU machines, tried to do the deep learning work. Then what's going to happen is saying, very typically what you do is using this Hadoop or Spark or those things to cranking to the pre-processing your data, right? You put the data in a certain format, and then ship them over to the other side. Say now you apply your TensorFlow applications to do some modeling. Then you come up with some model result, and then say, okay, let me apply the model. For example, let's say you come up with the deep learning features for your other application, like let's say Flickr, right? We do the tagging of our pictures. When you do those tag of our picture, we tend to using the deep learning to have deep learning features in addition to those simple features. Then you come up with a set of tag. So in the last stage, we will apply the some Spark algorithm in it, right? So then you could see like all the data movement, the model movement is also happening, right? Then, so what we're going to see is that a lot of complaints from our deep learning guys say, oh, your pipe, the network is causing trouble. I do not get enough data. Something like there's a lot, and especially if when you do the deep learning, you do lots of experimentations. It's not like you from day one, you have the best model you could potentially have just to do the job. You need to going through this thing many times. Then you could see the lots of frustrations you could build up if you have separate clusters. One for those normal machine learning data analytics things, and the other ones for your deep learnings, right? So that was a kind of a logical, it's a conceptual problem we tried to solve. So then the solution is simple, right? Solution is they say, why don't we put this thing on a single cluster? So in the simplest way, you imagine that you have a cluster that a cluster, if you could run the Spark job, then why don't you do all other things? You do the ML lab there, you do the cafe there, you do the TensorFlow there, you do the Spark SQL there, you just do everything over there. Then once you have those, for example, your data scientist could just jump into a Jupyter notebook, for example, right? In that notebook, you could do a lot of experimentations just on that notebook. You know more worry about the data movement, no more worry about the separations, you know more worry about the lack of the computation resource or lack of data. Everything is available for you for your job. Right? Sounds good? Decent, right? Okay, so then the other thing we wanted to do is, as a part of the design principle we put in place was, you could do, many potential design patterns you could put together. One thing we said was, one of the important constraints for us was, if whatever the code we're going to write on the TensorFlow on Spark, they should be almost have a zero overhead caused by us. We wanted it to be as efficient, as scalable as a dedicated TensorFlow cluster. So as evidence, I think when we released our open source code, I think we did little bit like a benchmark of the, I think this I think was a GoogleNet. So essentially, we show the thing, if you look into this thing, this I think if you could find a very similar matrix just on a standard TensorFlow things, right? So I think we verified it's actually like that. I think you certainly you are welcome to test out. Okay, so that's again I think it's also the near linear scaling those things. Those are not really a capability introduced by TensorFlow on Spark. That is the great work TensorFlow community has put together for us, right? We simply try to say, just make sure we are not introduced overhead on it. For example, if you could, for the people who know the Spark, right? A very simple design pattern many teams do is that you have a driver and have an executor do the job. In a typical Spark applications, executors, they never talk with each other. Then imagine you apply that design pattern to TensorFlow distributed learning. Then what's going to happen is for each, you do the mini batch, right? You mini batch, each of the executor going to do the work. After the mini batch, they need to somehow synchronize or asynchronous, somehow exchange informations, right? And if you do a typical Spark design patterns, all the information you need to go to the driver. Remember Java is a single process. And think about how much computation bottleneck is that guy going to cause, and the network bottleneck, everything going to be caused over there. So we basically we're not going to go down that path in order to achieve this thing, right? So anyway, so that's kind of the thing. So and then another design we try to focus on is if you know how to write TensorFlow applications, or even if you already have a TensorFlow applications, we wanted to minimize the number of code you need to change for the migration to the TensorFlow on Spark. I think in the open source, the README document I said less than 10 lines. You know, I don't know if that 10 line basically is the concept, right? So you know, you want it to be just quickly enable you to do the job. And then the other side, you know, from the TensorFlow point of view, there's a lot of capability in it, right? You could do the synchronous distributed learning, you could do the asynchronous distributed learning, you could do the data parallelism, you could do the model parallelism, all those things. We say we want to support all of them. Right? On the other hand, you know, remember it's a design pattern like the normal Spark design patterns. Imagine how you're going to do the asynchronous distributed learning. That's almost impossible. That's why all the other framework, you know, before us, people to put it together. For example, there's the effort called the TensorFrame from our friend from the Databricks. Like that is the only support the asynchronous, only support the synchronous learning, right? You cannot do the asynchronous learnings, and then you know you cannot have the parameter server like things that provided by the TensorFlows. Then another thing is if you know that in the TensorFlow, many of users you love your TensorBoard because that is a kind of visual thing that let you peek into like what's going on in your training process, you know, because your typically your deep learning job going to run for a while, right? And you wanted to know, does my set of the high parameter or my network topology is there converge at all? Then that's a TensorBoard is a visual tools enable many of your data scientists to see what's going on. So we say we need all those things. Then certainly, you know, without explanation, mentioning, you know, we want to enable all the Spark capabilities and the TensorFlow thing, just mix that together, right? Okay, so the implementation, what we did was basically it's a PySpark wrapper for the your TensorFlow things. And then what we do is going to launch using Spark. In some way, it's a concept already in the basic level, we're using Spark as a way to launch a TensorFlow cluster. Then after that models, you know, we could decide, you could say, after that Spark should even not in the picture. But there are the cases that you want to Spark in the picture. So for example, let's say you want to, you want to use an RDD type of things, right? RDD data frame type of things. So for that reason, in the TensorFlow on Spark, we support two modes. One is have Spark to pushing the data into the TensorFlow. That we call we will work on using the feed dictionary concept inside TensorFlow. Then another side is enable the TensorFlow just suck the data out without Spark's involvement. So that will like using Q-learners or things. So anyway, and then during the work, you could using the TensorBoard during the trainings or after the trainings. We have all the information enabled for you to do the work. Then, by the way, we do not really care about which particular version of the TensorFlow version or Spark versions. We did a very simple work that enable you to do all the versions. Right. So here's the visual thing, right? So essentially, from your Spark drivers, we basically say we're going to launch your TensorFlow applications or your parameter servers inside the Spark executors, right? So if you think about it, so they get launched. Then the only strange thing we are doing here is say we enable those Spark executors talk with each other. Because if you just look into this borderline portion of the things, that is the dedicated TensorFlow cluster inside the Spark. Yeah.
If I'm not mistaken, one of the major points underlying resiliency for Spark is that an executor can fall lost its data. This data will be recomputed using its lineage. So there is a fundamental assumption in Spark that resiliency relies on that. If executors start talking to each other and stalking state, because TensorFlow is stateful, on the contrary of
I think you're getting into the question about how you're going to deal with failures. Can you wait a little bit? I have a slide on top of those. So that's the idea here is to say we want to, so this design pattern is enable, so once you're launched, after that you have a dedicated, essentially you have a dedicated TensorFlow cluster, right? Then you could do whatever the job you needed to do. And then normally you could using gRPCs, that was the default implementation of the TensorFlow for the communication between the TensorFlow process. As a part of our release, we introduced the RDMAs for the infinite band network. I think that code now is a part of the TensorFlow, from the TensorFlow now. Really, I think you could consider that to be outside the scope of the TensorFlow on Spark. And right, so that's kind of the conceptual picture, right? So this is like not a traditional Spark applications, and then we tried to achieve the goals we set. Right, then during the, after you launch the job, on your driver log, we will print out the URL for your TensorBoard. So you could just jump in there, that TensorBoard. You will see, look at the graph, look at the convergence of all those things. Just all those capabilities of your TensorBoard is available for you at your fingertip. So in order to do this, when you launch the job, you need to simply say, I want the TensorBoard. That was the flag you need to turn on. Okay. So again, TensorFlow on Spark is very basic, right? You launch a TensorFlow cluster, let's feed the data, do whatever, do the training, do the inferencing, even to the shutdown. So that's the kind of basic, very basic thing. So because that's a very basic thing, so your simple API will like this. That's the basic API, right? Run a cluster using a Spark context, using my functions that do the real work. That's a map func. That is your logic, your TensorFlow code. And then a bunch of the arguments you want your function to take. You specify number of the executors you want. And then among those executors, how many of them you want to declare them to be the parameter servers. Then there's a flag to indicate, say, you want TensorBoard or not. And then there's the input mode. I will explain to you, its logic is does the Spark push the data, or you will taking care of does your TensorFlow code taking care of get the data or not. So once I have that, you could do cluster chain. If you're using the RDD, you're using RDD things. You put your RDD over there. You do kind of the training, inferencing things. At the end, you shut down. So that was our original API we introduced from day one. Then, so next few slides, I'm going to show you something new. So hopefully you will like it. So this has, in the last several months, my team have been working with our friend in the Databricks. Right, so you guys know that the effort is Databricks guys announced this thing called the SparkDL, Spark Deep Learning something. So this thing was SparkDL only do inferencing, does not do training. And then currently the SparkDL implementation in some way was, it was not generic for all the data, it's mainly was for the image side, right? So we saw the collaboration with the Databricks team was to say, let's come up a pipeline-based API that enable you to do all the trainings and the inferencing. And so here's the training API. So we call it the TensorFlow estimators. again, you saw your map functions. That's like your logic. And then whatever set of arguments. Then we have a bunch of the parameters that enable you to set. Essentially, that was like the normal pipeline thing, right? You need to say, okay, at the end of the day, for the training, you need to provide a data frame, right? So for the model training, you're going to fit with the data frame. Then you need to tell how inside how that exactly those data frame columns be mapped to placeholder in your TensorFlow code. So that was this set input mapping things. So like your data frames column somehow all magically mapped to this tensor name in your graph, your input side layers. And then the same thing somewhere where they put the output mapping. I did not mention here. So anyway, so you do those. And then you need to specify, how big your, now we call it the set cluster size. That's like how big your thing is. And set the number of the parameters. You specify where you want is the model to be checkpointed. And then if you decided to, you could use the saved, so there was this thing called the saved model. And that was like the checkpoint and the saved model. And the saved model tended to use it for serving things, right? So you could specify the location of the saved, your saved models, and a bunch of other hyperparameters you could set, like batch size, all those things. And then you do the job. Right. So with this, you should be able to do like all the things you need to do for the training. Then, so here's the inferencing side. So if you think about the inferencing, there are two typical use cases. One is I using that graph, I just run the thing to the whole end, and you do the prediction thing. So that was the top ones. So that one, again, you use the model transform. So that's again, assuming you guys know the MLlib pipeline API. Yeah. So the transform is like the normal thing, right? So that is when you're giving an inference data frame, input data frame, you're going to go against it. Then you set the input mappings, the output mappings. The output mapping here is the first one is the tensor output tensor name, and then the column out over there here is the value over there will become the column name of your result data frame. So you do that. So one thing you notice here, for the inferencing here, you write 0-line code. We do not, as long as you tell us where the model is, you do not need to write any code. And then another use case you may want to do is using the deep learning to TensorFlow models to do the produce the deep learning features, right? So that we could featureize this. So the only difference between that one and this one is saying you pick different sets of the tensors. Like let's say you have 10 layers or 100 layers. You pick some middle point, some layers. Say that's the feature I'm going to use for my things. So you just specify the output mappings in that guy. Sounds simple, right? So then so for the more sophisticated people here is the thing. So we also want to support both the checkpoint and saved models. So when you're using checkpoints, you make sure you specify the set model directories so that it knows where the model is. I mean, if you trained either, whatever, look at your code, make sure it knows where this that model thing is. Or this one, I think I typed. If you're using the saved model, you make sure you set the export directories. So that one is going to be used. And then when you do the saved models, you typically, when you in your TensorFlow code, many times you specify the signatures. Because that was the signature used by the TensorFlow serving for the gRPC calls. So we enable you to using that or not using it, right? So if you could, if you say, when I did the training, I did not know what people are going to do with it. or on the I define a few things. Maybe those things I do not like. Then you just do this. On the one hand, you say, no, whatever the signature the guy trained for me was good enough. Then you could specify this, signature def keys to point to that guy. Then you are done with it too. So that's basically kind of the basic concept. So in the nutshell, we enable you to do the trainings, any type of TensorFlow code, by embed your code inside, either using the basic APIs or the estimator APIs. For the inferencing, we do not need your code, just tell us where this thing is.
Does this work even if the inference and the training are completely different apps?
Yeah. So that's why it's the beauty of the thing here, right? So imagine here, right? We just need to say, where your file is. Where is the model file? Let's say you did the training on your single laptop. You're here. Then you say, I have that thing. We have lots of data. I'm going to crank into the predictions. So put that file in wherever it is, in S3s, in HDFS, then point it to it. Then you're using this API that's, do a lot of data, prediction, visualizing, whatever you want to do.
So checkpointing is not only about resisting failure, it's the official way to save.
Yeah. So what happens so in the TensorFlow code, in your TensorFlow, when you do the checkpoint, it's checkpoint all your the values of your parameters at that point. So you could just take that thing out to do the work. So in the early days of the TensorFlow, there's no save the model concept at all. There was only checkpoints. The save the model concept was introduced when the TensorFlow tried to cover the serving needs. So it depends on what you do in your there are two types of the application, TensorFlow applications. The early ones, if you look at their examples, there's no saved models. Then the later ones, they started to add the saved model. We basically say we enable you to do both. Take those things, pick a one, you go for it. Go for it. So again, I think we said this is two models, right? I said let me just cover a little bit so that we could answer your failure questions. So the one model is to say, let the TensorFlow taking care of everything, right? So once you launched, do not bother me anymore. So here's the architecture, right? So we basically inside the executors, we are launching a bunch of the Python workers, right? So then you will, based on your specifications, some of them will declare as the parameter servers, and others declare them to be the workers, right? Then after that, we say, let's, establish the network between them so that we form a nice, beautiful TensorFlow cluster. Then we say, let the workers take the data from HDFS or whatever they want from the queue runners. Right? So that's kind of the thing. So let me just answer I guess I could answer the question here. In this case, if the executor died, they will be replaced. And then all your model, whatever the checkpoint things will be, added on HDFS. So really, say whatever the latest model you will be keep carried on. And the new executor will launch. They will take new data or whatever the data they need supposed to take, then go from carry on over there. So then from your coding point of view, it's really, in addition to the other things, I think one thing I did not mention is that essentially there's one line of the code change in your TensorFlow logic. So normally in your TensorFlow code, somewhere you say start my server, right? Somewhere say start my server with this set of the TensorFlow cluster specifications. So replace that line by this saying context start cluster servers with then that's it. So we already pass, so thing here is that magic object we are passing you in your call called the context. Because that guy didn't know like a whole, like all the setup of the parameter we passed on, for example, like you earlier on passed me into the run function or is the estimator function, so we already have at hand. Right? So again, our goal is to say minimize the number of the code you need to write or change. So you could check out, for example, this code. Try to check out like this guy here, right? So that was the MNIST, dist, Python code. Look at that, you see, this is just a normal TensorFlow code. So then the other mode we support is the Spark mode. So more or less kind of similar. You launch your Python job workers. Then, some of them we declare with parameter servers, others we declare to be the workers. Then the very small thing we are doing here is between your worker. So now the worker actually we are launched in a separate process inside that execute environment. So you have the Python worker over there. So the top of Python worker is your Python Spark worker. And then the queue here is enable us to connect the Spark side of thing and the TensorFlow side of things. Again, so you accept those, the TensorFlow workers, TensorFlow Sky, they connect as a cluster. Now, the Python worker side, so you get the RDD stuff, right? So then what we do is essentially we put also the data into the queue. Then the worker essentially going to ask, say, give me next mini batch. So that's it. So for this guy, the failure conversation is slightly more complicated. And one side is to say, if let's say my Python worker died, and that, Spark will taking care of the failure over things, right? It's going to launch new things, that whatever the partition has not been processed, going to launch into a new executor is just doing the job. On the one hand, let's say if the worker died, we have a little bit more challenge because the Spark do not know what happened. So again, for this scenario case, instead of asking you to change one line, we actually need to ask you to change 3 lines models. So you need to start your cluster server things. Then somewhere because we needed to have to pull in the form queue. So we say calling this API called get data feed. That's logically give us that pointers or something. And then later on, whenever in your while loop when you do the training, right? Then you need to get the data. So then here you need to say call the next batch with our feed object we produced here. Does it make sense? So you start up your server, and you get the handle of like something so that I'll be able to get the feed your data, and then in your while loop here, because you kind of say all the mini batch you're going to say, okay, give me next mini batch, then I do forward backward things. Then you do all those jobs and do the session run thing, right? So then you're going to keep going through that loop. Instead of 1 line, you need to change 3 lines. Then again, you could check out the Spark version of the MNIST dist Python code. You could check out with it. Okay, so I think we kind of covered the failover things. I think one thing, so there are a few things just recap. So we in the code on the cover, we try to do the checkpoint into HDFS. That's all current implementations. So if a particular machine died, that's okay. Whatever thing you trained, your checkpoint of your TensorFlow state is on HDFS. That will be carried on when a new executor launch being doing those. And when the conversation is much easier when you're using the TensorFlow mode, because all those things is like, it's just by Spark capabilities, we will launch your new executor, all those stuff. Then in the Spark mode, there are a little bit unknown things here. That is could be a problem you need to look after. But we have at Yahoo, we have been using this TensorFlow on Spark for last over 1 year. I think this has not been a significant problem that my team had need to worry about. But if it's become a problem, I think please jump into the mailing list. There's any issues. I think we will see what we can do.
That, practically, you are using the input mode Spark at scale without significant issues.
Okay. So I think let me just wrap up. Like it's a simple thing, enable you to do the deep learning on Spark cluster, and we support all the different versions of the TensorFlows and different versions of Spark. And currently, we have tested it on Yang standalone methods a little bit. And we also have the older version of the, you could run this thing on EC2. They have the image provided, but likely that the image need to be updated. If any of you wanted to follow our instruction, build an image, that would be great. So that's it. So we want to thank all the open source community, Spark, TensorFlow, and Yahoo let us, to do some fun job. And then everybody, I don't know, anybody here contributed to our code. But, we have check out our stuff. Any questions?
Do you need to install TensorFlow on executors?
Yeah, so you do not need it to. So please follow our instructions. So the way in our case, we're using Yang. So at Yahoo, we're using Yang as the cluster managers. So what we do is when we only install the TensorFlow on our gateway or launchers. And then the instruction we give to you is we will ship also the TensorFlow thing as an archive, whatever, to the executors. So after they finish the job, nobody know you ever did anything TensorFlow.
Okay, great.
Yeah, go ahead.
Have you dealt with different versions of Python on your?
Yeah. That's a good question. Yeah, so because the TensorFlow is written in Python, and then many different users want a different version of Python. It's a nightmare, right? Yeah. So what we did was at Yahoo, what we did is we support 2.7, 3.5, 3.6. Everything else we do not care. So one thing I think I would like to see is I saw was the release from the. Have you guys watched out the AWS SageMaker? Right? The thing sounds like what they do is like almost a logic you create a Docker image type of things. So you enable you to deal with that thing. You say, okay, I pick a particular TensorFlow, a Python version, then particular set of the modules you wanted to use for the Pythons. I think it is annoying things, but I think it's not something we have publicly provide any solution to it. It's a very known Python problem, I guess. Yeah. So what we did was so at this moment we made the TensorFlow on Spark as a service inside the company. We do not want anybody to install the kind of things. We say here's the default set of the options you have. You just go to all, for many of our data scientists, they jump into the notebook. And the one of the choices you need to pick is to say which version of the Python you're going to use. After that, they're just doing all the standard Spark job, TensorFlow on Spark job, all those things. Go ahead.
And you guys have Jupyter connected to Yarn?
Yeah.
Okay, so then they can just...
So that, by the way, that piece we have, maybe I don't know, I could talk about it. Whatever. This is my last week for the company anyway. So the way we did was when we started this deep learning thing, right? The TensorFlow was really, really popular, I have to say. Inside the company, all the data scientists wanted to put their hands on TensorFlow, on Spark. And then the thing was this, so what we did was then we say, okay, let's, but many of them also love the notebook thing, Jupyter Notebook. The thing what I personally want is want our data scientists to collaborate with each other, right? So what we did was say all of the Jupyter Notebook will be saved into HDFS. So the URL we have all this Jupyter Notebook. As the last portion of that thing actually is our HDFS path. So let's say you did a good job for come up with a good experiment of your deep learning things with your notebook. Then you could pass along that URL to whoever you want. Then they will be able to look into your stuff. Go ahead.
And you were mentioning Jupyter Notebooks. Were they running PySpark and everything was going in PySpark and TensorFlow? Or do you have a mixed, let's say, Scala Spark feature engineering, which then gets connected within the same application to TensorFlow stuff? Or is it distinct applications communicating by just dumping intermediary results on?
So I think they have the extreme use case of the certain user was they have each notebook when you start, you need to select a kernel. That kernel will be either Scala or Python things. So what we enable them to do here is say, let's say I'm using Spark, Scala kernel to do using my normal Spark things to produce something. So at the end of that thing, we have some data frame on HDFS. Then they will create another notebook, say I have my Python notebook, and in that guy, you will use the TensorFlow on Spark. By the way, we are about to, we have an early prototype for the TensorFlow on Spark, inferencing only in Scala. Do you want it?
Oh,
yeah?
I want to know about
Okay. So because the thing because we thought I feel I do not want to do the training. You know why? Because so many TensorFlow operators, the training operators, their logic is written in Python side. So I do not want to do the nightmare, go after Google guys or whoever wrote in those Python code, move them into the C++. But for the inferencing itself, it's just a C++ code. So if you guys think that's an important thing to do, I think I could push the team through, make it work. Yeah? I see all the smiley face.
Let's talk a bit more about that offline.
Okay, cool.
Yeah.
That's good. I thought it was, all the small features we could integrate. Go ahead.
What is your experience with dealing with large model sizes in the prediction part? So once you get a certain size, you have a very big model, how do you distribute it on Spark?
So the currently, essentially the answer here is, so if you wanted to do the large model inferencing things, currently you could write your code if you are brave enough, right? You have your originally in the training time, you have multiple parameters. You extend your code to using those multiple parameters. So you could do that. But if you wanted to say, I want to do the inferencing outside of TensorFlow, my Python environment or Spark environment. Let's say you wanted your edge serving things talk with it, right? Then in that scenario, you do not want using, a Spark thing, right? So for that scenarios, I think there was I actually asked that question to the TensorFlow serving lead in October. That was a Google Fall symposium on the TensorFlow. he said, so he's currently, he was saying, and you are the first person to actually ask for it. Nobody in the Google has been asking me that. So he was excited. So the way his proposal was, you end of your graph was big, right? So he was asking, suggesting you cut your graph up to like have the container graph and the subgraph, and put this subgraph in the mode.
So you shard?
You kind of, in some way, you shard your graph up. I think it did little bit agree. I think I have to say, he's kind of dreaming what to do. I think, we should push him.
Yeah, how do you know which shard to go to for?
Because you're controlling it, right? Because you're cutting it.
Oh.
You're cutting, like you have the top ones, all the requests go to the top gRPC servers, so the guy know who are my remote ones, kind of thing. So you could do those. And then the other way stuff I was trying to do, even like I say, what if, let's say for your edge serving, right? Let's say imagine you wanted to run through thousands candidate ads through this deep learning notebook and to rank them. So in that scenario, I think you not necessarily want to use the Google TensorFlow serving gRPC implementations. Because if you send those thousands of them over the wire, then you're going to be screwed. Right? Yeah. So I think hopefully in next several weeks, or maybe we will show you some code. So we have another project called the Vesper that was all in, like with search engine things developed by our Norway team. So I have some pep project going on with the lead architect on that thing. Hopefully, that was the thing. I would say, if you think about a search engine, inside the search engine, what if you want to do those things? So that was another way to solve the problem. I guess that's it. I think that overall, I would say TensorFlow serving, how to serving a TensorFlow model is an interesting problem to solve. Yeah.
Actually, there is, it does not address the inference on large graphs, but it addresses partially the inference in a completely different environment. Typically, web server, real-time web server instead of offline cluster. There is the MLeap project, which pretends, I've not validated that, but they pretend to be able to convert a trained TensorFlow graph to a technology-independent representation, typically a zip set of protobuf and JSON file with a pure JVM player, which is able to interpret that efficiently, so that they can use a trained TensorFlow model on a backend cluster and deploy it not in a TensorFlow specific form, which requires Python, but in a platform agnostic version on their web server.
Which company?
It's the company is a small startup split off from TrueCar. The company name is CombustML. They provide a commercial model serving technology based on that, but the MLeap component, which does that, which specifies the format and which proposes exporter from scikit-learn, Spark Pipeline, and TensorFlow, is an open source component. They only made a closed source serving infrastructure.
I think there was another effort too, right? There was what's the ONNX? You guys know?
No.
This is the Open Neural Network Exchange format.
Oh,
that was started by our friend in the Facebook.
Really?
Yeah, I think at this point they declare, the MXNet, what's this? CNTK. They have somehow, and Cafe2 and PyTorch.
ONNX.
Yeah. So there is that effort as well. And I think the little bit over there is the TensorFlow side, they do not care. Like all those, like the leader, all those things, same thing, right? If the leader does not care or exchange. All those the competitor, try to say, let's exchange with you, kind of things. I think the overall, I think there's a lot of work one could do on this serving side. I think the trouble to me was, how you come up with models. Because this world is so dynamic, like new operator get introduced all the time, right? Then how you come up with things that, everybody going to agree on. I mean, what they did, the ONNX thing did was they have a small number of operators. They like frequently used operators, they define it as semantics, and then enable like to the exchange. But on one hand, if you look at the total number of operators, many source framework has, it's way more than the things. I mean, but on the practically, maybe that's good enough. That's it. Thanks.